Chapter 26, and we're going to talk about sound. And the big idea is the idea that sound is simply a form of energy that spreads out through space. So when you hear a singer or somebody, what you're hearing is these molecules vibrating as that sound is transmitted. So sound originates through vibrations. And, probably the best example of that is if you see a tuning fork, and if you see it, especially if you see it like under a strobe light, you can see how it moves back and forth all the time. And that's what sound is. It needs some kind of vibration in order to create that. So whether we're talking about a piano or a violin or a guitar, every single one of those has a vibration. A saxophone, the reed vibrates. And a flute, you've got a column of air that vibrates as the person blows air over top of it. So even when you talk, that's a vibration of your vocal cords. Everything is due to vibrations. And one of the interesting things about all that too is not only is there a vibration of those particular objects, of the the chord on the string on the guitar or something, but it also causes something else bigger to vibrate. And so, like if you have a guitar, you've got the sounding board that goes with it that causes larger amounts of vibration so that you can hear it. Or if you're talking about a reed, there's a column of air that's going to vibrate. Or if you're talking about talking the air in your throat that vibrates, and that causes that to be louder for you to hear. If we're talking about pitch, pitch has to do with frequency, and the higher the frequency, the higher the pitch. The lower the frequency, the lower the pitch. Typically, a person, especially a young person, can hear a frequency of somewhere between 20 to 20,000 hertz. 20 being very low, 20,000 being very high. As you get older, that hearing shrinks. You don't hear quite as high. Anything below 20 we would consider to be infrasonic. Anything above 20 is called ultrasonic. Now, while we can only hear up to about 20,000, other animals can hear a lot higher. Like a dog can hear up to about 40,000 hertz, which is why you can have a dog whistle, which is something that you can't hear, but the dog can, because they can hear a lot higher frequencies than we do. Or a bat, which can hear up to 100,000 hertz. And so a bat actually sends out very, very high sound waves that, sonar basically, that they bounce off of objects around them, and that's how they see, in a sense. That's how they detect where they're at. All right, section 2, oops, sorry, didn't mean to say that. Section 2 is sound in air. So we're talking about how we get air traveling, and we're going to talk about compressions and rarefactions and so on. And you've all, if you clap your hands, you're going to hear a sound, and that sound pulse is going to go out. It's going to go out in a sphere away from your hands. And as it does that, particles in the air vibrate to carry that sound from your hands out to the edge of the room, basically. And sound is a compression wave. So remember when we had the slinky and we pushed it, back and forth, that would be an example of a compression wave, just like sound wave is a compression wave. And they kind of use this example of, let's say that you go into a room like this. You've got the door on one side, you've got the window with a curtain on the other side, and as you open that door, you move the air, and so that causes that curtain to move out. And as you close the door, you pull that curtain in. So moving the door in would be called a compression. When you shut the door, that'd be a rarefaction, because you get less air, less particles in that area. It creates kind of a vacuum as it pulls those things out. So this pulse, is a compression that we talk about, and as the air pressure is less, we call that a rarefaction. That pulse, when we're talking about sound, is what travels, not the actual air itself. The air, it might move a little bit, but it's not going to move across the room. So when you're hearing this sound, the air that's next to your ears is vibrating, and that's caused by air that's just a little bit farther away, that's vibrating all the way back to the source of the sound. But the air itself does not move across the room, just the pulse, or just the energy of the sound that moves across the room. And the same thing is true when you have a vibration like a tuning fork. It's just like the curtain moving back and forth. That tuning fork moves back and forth, and that compresses the air near it. And what happens is the tuning fork, the tines, I guess, would move away from each other, and then they're compressing the air. And then as they move back in towards each other, then that would be where the rarefaction is. And in a tuning fork, that's going to happen very, very quickly. Your tuning fork is going to have a certain number of hertz, and it's going to be maybe several hundred times per second that's going to vibrate. Okay, so let's talk about how sound travels through various mediums. So, we're used to hearing sound. It travels through air, but sound will also travel through solid objects. If you put your ear on a fence and somebody taps down the line on the fence, you can hear it. It actually moves faster. It's louder. Same thing if you're underwater. If somebody makes a sound underwater, they give the example of clicking two rocks together. You're going to hear that underwater just like you would if you were in the air. In fact, it'll actually come faster underwater than it does in the air. The speed of sound varies depending on what sound is traveling through. So it travels faster in liquids. It travels even faster in solids than it does in gases. But it has to have some type of medium for it to travel through. So in this example, if you have this bell in it, or this bell, and it's in a jar, and this is a vacuum jar. They have a vacuum pump pumping out air. When you have air in the jar, you can hear it, and then as you vacuum, as you take out all the air, then you can no longer hear the bell because there's nothing for that sound pulse to be transmitted in. So you can't hear sound in a vacuum. So if you're out in space and you yelled, nobody would hear you. If we're talking about the speed of sound, that's going to depend on a couple of different things. It's going to depend on what the material is we're talking about, and that material's elasticity. It's also going to depend on the temperature. So, you guys have all seen where you see like lightning, and then you don't hear the thunder for quite a few seconds. And typically, what you find out is if you see lightning, and then for every 5 seconds that you can count, that lightning is roughly a mile away, because sound travels so much slower than light does. And so, that has a certain speed to it, considerably slower. Remember, light is traveling 300 million meters per second. The speed of sound in air at 0 degrees is 330 meters per second. So that's quite a bit slower. 330 meters, if you kind of calculate that out, you find out that that's going to be roughly 1,000 feet per second. And so we know that there's about 5,000 feet in a mile. That therefore takes about 5 seconds for that sound to get to you. Versus the 1/1,000th, or the compared to light, it's about 1/1,000,000th of the speed of light, and so therefore the light gets to you much, much faster. It's like at a track meet. They always tell you to start your watch when you see the light, when you see the flash, versus when you hear the sound, because you're going to be a couple of tenths of a second late if you do that. Sound does vary depending on the speed. Sound speed varies depending on the temperature, and it goes up roughly 0.6 of a meter per second for every degree above 0 degrees that you are. Also depends on the mass. So if you have something that's heavier, hydrogen molecules and helium would move faster than would heavier gases such as oxygen and nitrogen. And, just think of it as, in order for these vibrations to be carried, those objects have to move back and forth. Lighter objects, a little bit easier for them to move back and forth. In terms of things like solids, it depends not so much on an object's density, but on something called elasticity. How much can that thing bend and snap back quickly, basically, is what we're talking about. And steel, for instance, is something that's pretty elastic. I mean, you can actually stretch steel. It takes a lot of force to do it, but you can do it. But when you release that force, then it's going to snap back to its original shape very, very quickly. On the other hand, putty isn't very elastic. So think about something like putty or Play-Doh or something, and as you pull it, you can pull it and then let go, and it might slowly go back, but it's not going to snap back very, very quickly. Something that snaps back quickly would be more elastic, and and that would transmit sound waves a lot faster because, once again, those vibrations have to transmit through. So it has to go, come back, go, come back. It goes, vibrates back and forth. And in order to do that, it has to be, the more elastic it is, the faster it'll do that. So if we're talking about steel, sound travels in steel about 15 times faster than in air. And sound travels in water about 4 times faster. And that's why you saw, if you look at the old movies, they always put the ear on the railroad tracks to hear if a train's coming, because the sound would travel faster and they could hear it from farther away when they do that. All right, so here's a question. How far away is a storm if you note a 3-second delay between a lightning flash and the sound of thunder? And suddenly they're going to jump to the speed of sound in air is 340, and that's about 20 degrees, I think. It's somewhere in that area. But anyway, they're telling you that at whatever temperature it is, it's 340 meters per second times 3. It's going to be about 1,000 meters per second. I still, for us, it's kind of really simple to think about in terms of feet, because it's roughly 1,000 feet per second. And so you could say, oh, well, it's about 3,000 feet away, a little over half a mile.